in chapter 7. All right, so you've already done 1A, so let's look at 1B. We are going to find the dimensions of a rectangular garden whose perimeter is 100 and whose area is 300. There are lots of ways that you could work on this, but at this point, right now, I don't know anything about my width or my length. Do you agree with that? No. That's what I'm trying to figure out. I do know that perimeter is 2 widths and 2 lengths. So does that equation make sense to you just from the problem? And I know that area is length times width, and I know that equals 300. So I've got 2 equations, right? And I need to figure out, I need to solve this system. So let's look at that. I think substitution might be a good idea. I could, and again, you've done this a lot, you do whatever you want, but I could say that L equals 300 over W, that's a true statement. And then I could put that right here. Substitution. So 2W plus 2 300 over W equals 100. I might just divide everything by 2 just to make my numbers smaller, but what do I do now? What am I going to do now, Sammy?
That's a quadratic, so you can subtract 50 over.
And multiply everything
by W.
So W squared minus 50W plus 300 equals 0. So Sammy noticed that I got to clear this fraction. That's kind of standard procedure. And when I clear it, I'm left with a quadratic. So he said, let's move the 50 over. So now it's like in standard form. Does it factor? I don't know. I could sit here and stew about that. Maybe it'll occur to me, maybe it won't. What else could I do though, if I don't want to waste a bunch of time on this? I could use the quadratic formula. I have my calculator. So it just might factor. But I don't know. So, actually I think it does. 30 and 20. No, that's not right. Never mind. So W equals negative B plus or minus the square root of B squared minus 4AC all over 2A. All right, let's see what we come up with here. Quit it, don't even think about it. I don't think that did factor. I got 43.03 from one of my answers, but I could be wrong.
I got it.
You got that too?
Same
All right, and then my other one.
I prefer walk in the rain.
I got 6.97. Stop it! So your job is to figure out what the dimensions were. So W is either going to be 43.03 or W is going to be 6.97. Right? So what does that make L? Well, L is 300 divided by W. So what happens when you do 300 divided by 43.03. Oh my gosh, what do you get?
6.6.
Yeah, so those are the two dimensions. We don't care which one's width and which one's length. What are the dimensions of the rectangle? 43.03 by 6.97. Those are the dimensions. All right, C. What's happening in letter C? We are solving this system. What's your thought on that?
Divided by 3.
Actually, we could just set them equal to each other, couldn't we? Since they're both y's, we could do what you said, absolutely. But since they're both equal to y, can't we just do this? And we don't have any fractions or anything. Now what? Get it set equal to 0, so x cubed minus 9x equals 0.
And then take out an x. And
Take out an x, factor in other words, so x squared, oh my goodness. So what do we got? X,
equals 0.
x minus 3, x plus 3? Because that's the difference of squares. So what does that mean? That means x is either 0 or 3 or negative 3. If x is 0, so is y. If x is 3, y is 9. And if x is negative 3, y is negative 9. Why are there so many answers to this problem? Erin?
Is the power, that's not the right word, but is 3.
Yeah. Geometrically or graphically, what shape is this? You know what shape that is. It's that, right? What shape is this? A line. So is it possible for a line to intersect that curve in 3 different places? Yeah, it absolutely is. All right, solve graphically. Let's get our calculators out. Now, we probably are going to have mode issues. You want to go to mode and change it back into functions. Because now you're graphing y's and x's, right? So you need to be in function mode. I think I'll just use a zoom 6, so a standard window, at least to get started. And then I'm going to see what shape I get when I type lnx and x squared minus 4x plus 2. Before you hit graph, I should have said something, but before you hit graph, did you kind of have an idea about what shapes you're graphing? What does a logarithmic curve look like? lnx, what's that look like? Has an asymptote, let's say I'm the y-axis. There's an asymptote at the y-axis, and then it comes up and curves out like that. And then what does that x squared look like? That's a parabola. So did your parabola and your logarithm intersect each other?
They did.
Yeah, so you know how to find the points of intersection. Second calc, intersect. Let's find them. .711 negative .34. Peter, did you already do both of them? Yep, 3.83. How have those looked, everybody? Is that what you got?
Yeah.
Perfect. So, We've solved some with substitution, we've solved graphically, we've solved with elimination. We're gonna do a couple more eliminates, and then we're gonna talk about matrices. All right, so let's look at question B. This is 3B, we already did 3A, so 3B. Now, with elimination, what's our game plan? So, we gotta somehow eliminate a variable, right? So one option is to multiply the top equation by -2, so you'll have -2x plus 6y equals, wait a second. Oh, I don't think it's 0 equals 0, is it? Did I make a mistake? I got 0 equals 8.
Yeah.
What does that mean? Which means what about my original two lines?
They're parallel.
They're parallel. These are parallel lines. There's no solution, no intersection. These are parallel lines. They have the same slope, but different y-intercepts. 0 cannot equal 8, ever. You know that. All right, 4x minus 5y equals 2, -12x plus 15y equals -6. Multiply the top by 3, do you think? So 12x minus 15y equals 6.
No, but is that the?
All right, I got 0 equals 0. Now, that's different than this, right? This is always true. What does that mean about my lines? They're the same line. Now, when you answer this question, don't say all real numbers, okay? That isn't what you mean. You mean every point that's on this line is also on this line. So those are the points that are the answer, right? All those points. So when you write your answer, let's write it like this. All the points, the set of all the points in the whole wide world, where 4x minus 5y equals 2. Because if a point is on this line, then it's also on this line, which makes it part of the solution. Right? You understand what I'm saying?
We could write
Yeah, either equation would be fine.
What does that line down the middle mean?
Such that, so that, so all of the points in the world such that that's true. All right, we determined that production and price of a new tennis shoe should be geared to the equilibrium point for this system of equations. All right, this sounds like an econ problem. The price P in dollars and the number of shoes X in millions of pairs. Find the equilibrium point. So, y'all know what demand is, right? Demand is how many of something you can sell, right? What do people want? What's supply? How many you got to sell, right? What do you think the equilibrium point is? Where they match, exactly. So you've got 160 minus 5x as your demand, and 35 plus 20x as your supply. So what are you gonna do? You're gonna set them equal to each other. You're gonna solve this system however you want, but in this case, it would be easiest just to set them equal to each other. I think easiest for me anyway. So I got x equals 5. Is that right? What does that 5 stand for?
Numbers.
5 million pairs of shoes. And what's P gonna be? Well, let's take our 5 back and plug it in. We plug our 5 back in somewhere. Looks like 135. what's that represent?
The price.
Of the shoes. So, this company is going to sell 5 million pair of shoes at $135 each. Alright, last one. By the way, the point in doing this is, it can be a word problem, but it's still so simple. It's simple, we're not gonna get freaked out by words. An airplane flying with the wind from Los Angeles to New York City takes 3.75 hours. Against the wind, 4.4 hours. So let's see, against is 4.4 and with is 3.75. Distance is 2,500. And I gotta find the airplane speed and the wind speed. Those are my variables. All right, got a plan, he's got a thought, he's got an idea.
Speed is miles per hour.
Speed is gonna be miles per hour, okay? Yeah, I think that's the distance between them. So they're flying to Los Angeles and then back, or I mean, from Los Angeles to New York and then back to.
You can just say X 3.75 equals 2,500.
Okay, so, perfect. So what Peter's saying is, this goes back to the idea that distance equals rate times time. Do we know the distance? We do, it's 2,500. Do we know the time? Well, let's do with the wind. Let's do with the wind. The time with the wind is 3.75 hours, would you agree with that? Now, what is my rate with the wind? You understand what with the wind means? It means the plane and the wind are going in the same direction. So I don't know either one of those two numbers, but if they're going in the same direction, I'm gonna do what with them? Add them together. So A plus W is my rate with the wind, and it takes me 3.75 hours with the wind. Now, can I build another equation for against the wind? Still 2,500, right? And that's 4.4 hours. What's this? A minus W. If you are flying against the wind, think about when you ride your bike or something, it slows you down. It slows you down, it's pushing you back. So what do we got here? We absolutely could set them equal to each other. Do you see a potential drawback, though, with setting them equal to each other? Then I would have one equation, but I'd still have my two variables. So you can absolutely do it. I don't think I want to because I don't like having two variables in my equation.
Factor it out.
Distribute it out?
Yes.
Okay, we could do that. I wonder, would it be easier to divide? I don't know, what happens if we take 2,500 and divide it by 3.75? Then I have to round it off. Alright, so 2,500 equals 3.75A plus 3.75B, or W. And then 2,500 equals 4.4A minus 4.4W. Alright, that's alright. Can we eliminate here? Yeah, it's not gonna be like beautiful, but we got a calculator, we can do it. If we wanted to eliminate the W's, what would we have to do? Top one by 4.4 and bottom one by 3.75. I have no idea. I'm just writing things. I have no idea. Does any of this look like it's on the right track?
Wait, when did you add the 11,000?
Yeah. Oh, yeah. I'm adding everything. I thought that was kind of slow for an airplane. Yeah. Oh, shoot.
I got A equals 5 equals 7.
Okay, are these two numbers right? Okay, is all that right? Okay, I didn't get 500 and some. I got 617.
That's right.
617.42. That's better. And then I gotta find my wind speed.
It's going against the wind.
No, this is his airspeed. That's his actual speed. And now I'm gonna find W. For my wind, I actually got 49.24. Did I get that, or did I make another easier?
I got that.
Okay, those were kind of yucky numbers, but since we had a calculator, it all worked out. Everybody get that figured out? Now, all of the problems we've done, all these have been like review problems from first year algebra and stuff. Everything we've done has been two equations and two variables. If that's the size system you've got, this is the way to go. Substitution or elimination, that's wonderful. But when the systems get bigger, like maybe 5 equations and 5 unknowns, like A, B, C, D, E, then this becomes a little bit tedious. You can still do it, but it's a little tedious. So, there are other methods that we can use to solve big systems, and one of those methods involves the use of matrices, okay? So we're gonna get a little vocabulary under our belt. So I'm just gonna put a random matrix up here. This isn't in the notes. I'm just gonna say a matrix D, and here it is. So, step 1, what is a matrix? A matrix is a rectangular array of numbers arranged in rows and columns. You gotta know that definition, okay? That's what a matrix is, a rectangular array of numbers arranged in rows and columns. Okay? So right there's an example of one. We generally use capital letters to name our matrices. I call this one D, it could be F, P, Q, A, whatever. And you can see it's arranged in rows and columns. Now, rows are like the rows of bleachers. Rows go this way. These are rows. Columns are like the columns of the White House. They go this way. So this matrix has 2 rows and 3 columns. Would you agree with that? Therefore, it is called a 2x3 matrix. These are its dimensions. The dimensions of a matrix are its rows by columns. Roman Catholic, rows, columns, always rows, columns. So when we say, how big is that matrix? Your calculator's gonna ask you. When we start doing matrix operations, very first question it's gonna ask is, how big is it? And you're gonna tell it, it's this one, 2x3. Those are its dimensions. The numbers inside the matrix are called the entries or the elements. So either word, they're interchangeable. Entries and elements are the numbers inside the matrix. So this right here, that's an entry. This entry right here, by the way, if I wanted to talk about that entry, I would label it with a little d, because that tells me it's in matrix D, and its subscript would be 2-1. Guess what that 2-1 stands for? Second row, first column. Always row, column. So when you put that little subscript on it, that tells you, okay, you're going to matrix D, and you're looking for the number that's in the second row and the first column. Okay, what do you think a square matrix is?
Same number of rows.
Same number of rows as columns, exactly. In other words, it's like a square room, the dimensions are the same. Same number of rows as columns. Is D a square matrix? No, it has 2 rows and 3 columns. A square would be 2x2, 3x3, something like that. There are things you can do with squares that you can't do with other matrices. All right, what do you think it means to be equal matrices? What do you think that means?
Same value.
Oh, I love it. I heard her say the same values, let's use matrix language, same entries in the same spots. Does that make sense to you? You can't look at 1, 2, 3, 4 and 1, 2, 3, 4 and say those are equal. They have the same entries, but they're not in the same spots. So equal matrices, 2 rules. First of all, they have to have the same dimensions. If they're not the same size, they can't be equal. And then they have to have the same corresponding entries. Same corresponding entries. So whatever's in the 1-1 spot in matrix A has to be in the 1-1 spot in B if they're going to be equal. Corresponding entries, same spot, same number, same spot. The transpose of a matrix is denoted with a capital superscript Z written up above. That means the transpose of the matrix. And the transpose of matrix D would be this. So tell me what the transpose of a matrix is. How do we build the transpose? We switch the rows and columns. Normally we say interchange the rows and columns, but if you say switch, I'm good with that. What was row 1 becomes column 1, and so on. this matrix stuff is a study of linear algebra, and there is a whole semester class that you can take called linear algebra. And our boys, in fact, Kate and Liam took it. It's all about this kind of stuff. And the transpose has many uses in that study. We're not gonna, we got a couple weeks to spend on this, but that's what the transpose is. We may not use it. A scalar. What is a scalar in vector land? It's a real number, right? What is a scalar in matrix land? A real number. The language of vector land and matrix land overlaps, because if you think about it, this is a vector, this is a vector, and this is a vector. So a matrix can be thought of as just a bunch of vectors all stuck together. So the language is the same. Identity matrix. Well, identities only exist for squares. So we could have a 2 by 2 identity. Any guesses what numbers are in there? We'll do 2 by 2 first. You say 1, 1, 1, 1? No. It's 1, 0, and 0, 1. Now, before you say anything, I want you to think back to vector land. What is 1, 0? What vector is that? That's I. That's the horizontal unit vector. Don't stare at me blankly. This was in the last, this was on your test. This is the I is the horizontal unit vector, and J is the vertical unit vector. So when we put the unit vectors into a matrix together, it becomes the identity. What would it be in 3 dimensions? Any guesses in 3 dimensions? What's that top row gonna be? Horizontal, 1, 0, 0. What's the middle row gonna be?
0, 1, 0.
0, 1, 0. And the bottom row? 0, 0, 1. Those are the, this is the 2 by 2 identity, that's the 3 by 3 identity. You could build them going on. That's what the identity matrix looks like. Mrs. Ford, how do we get the identity? You get the identity the same way you do with regular numbers. What is the multiplicative identity? Just the number that's the multiplicative identity in math. 1, right? That's the identity. How do you multiply numbers and get 1? What kind of numbers do you multiply to get 1? Reciprocals, or they're called multiplicative inverses. So if we multiply a matrix times its inverse, this is the result we'll get, depending on how big the matrix was we started with. Okay? Multiply matrix inverses. We're going to figure out how to find inverses. Okay. Next, identity, non-singular versus singular. This definition won't mean a thing to you because you don't understand what a determinant is yet, but just for now, for vocab purposes, a singular matrix is a matrix whose determinant is 0. If a matrix has a determinant that equals 0, it is called singular. Then what is a non-singular matrix? Its determinant is not 0.
What is the determinant?
But we don't know yet. We're going to figure that out. You might add to your singular definition. Singular matrix is a matrix whose determinant is 0, comma, no inverse. If the determinant is 0, it's what we call non-invertible. It has no inverse. Non-singular matrices, then, if it's not singular, it will have an inverse. Okay? And finally, the trace. The trace of a matrix only exists for squares. So I'm going to have to give you a square matrix here. square matrix, 3 rows, 3 columns. And the trace of that matrix, it's easy to get trace and transpose mixed up. So remember, the transpose notation is the capital T up here, like an exponent. And the trace notation is a lowercase tr out here in front. The trace of E, the trace of matrix E, is 1 plus 5 plus negative 9. So the trace would be negative 3.
So is it?
So, if you were gonna define that, you take, what entries do I add up? What entry is this? That's the entry in the 1, 1 spot, first row, first column. And then I add it to this one, what's that one? That's the 2, 2 spot. And then the 3, 3 spot, and it can be bigger than this. So I'm gonna say dot, dot, dot plus A sub NN. So if A is an N by N matrix, then its trace is gonna be it's 1, 1, 2, 2, 3, 3, and all added up, right? That makes sense? That's your definition.
So you can only do that on squares.
Only on squares, only exists in square matrices. Now, you can transpose anything, but trace and determinant and inverse only go with squares. All right, let's do some problems here real quick. We'll get a couple done anyhow. So here we go. Number 2, what are the dimensions of matrix B? Look at matrix B. What are the dimensions? 2 rows, 3 columns, 2 by 3. And we write 2 by 3. Don't say times, that's by, right? 2 by 3, just like a 2 by 4. Okay. All right, B, little c sub 3, 2. So look at matrix C, and we're looking for the entry that is in the 3rd row, 2nd column, and that is 3. A plus D. We want to add these 2 matrices together. Any guess as to how you're going to do this? Exactly! It is like so easy. 1 and 2, 3. Negative 2 and 1. 3 and negative 5. 4 and 3. There you go. That's it. Now, tell me what the rule is for matrix addition. Look at problem D. Problem D isn't doable. Because why? If you're going to add them, what? They got to be the same size. If you're adding corresponding entries, don't they have to be the same size? Yeah, so D is no solution. Can't be done. D minus 2A. Last one today. D minus 2A. So D is 2, 1, negative 5, 3. Now, what do you think I'm going to do with minus? I'm going to leave the minus. What do you think I'm going to do about 2A? What do you think 2A is about? Yep, it's like distributive. So here we go. 2, negative 4, 6, 8. Now, I left the minus. I'm going to subtract these. So I multiplied by 2. Now I'm going to subtract. Last problem of the day, here we go. What are we going to have? 0, 5, negative 11, negative 5. And that's it. I'm going to stop there, and next time we'll talk about multiplying, because that's a little bit trickier. Okay, perfect. me, Sammy.